Catharine joined Stellenbosch University as a lecturer in 2000, and in 2002 she received an Alexander von Humboldt Fellowship to study at the Philipps University in Marburg, Germany. This was followed by another visit to the same university thanks to a follow-up fellowship in 2010. In 2016, she received yet another follow-up Alexander von Humboldt Fellowship, and this allowed her to work with Tim Clark at the Friedrich Alexander University in Erlangen. Today, Catharine's main focus is the study of intermolecular interactions, combining her knowledge of computational chemistry and crystallography to explain unusual interactions. Catharine has acted as co-editor of one of the leading journals in her field and has played a prominent role in committee services and conference organization locally and internationally. Currently, she is the president of the South African Crystallography Society, and in this capacity, she delivered a presentation on this field in South Africa at the International Year of Crystallography at UNESCO in Paris. On top of all these research accomplishments, Catharine is also known as an excellent and passionate teacher, and she was awarded the Stellenbosch University Award for Excellence in Teaching, the Distinguished Teacher Award in 2017. But I think Catharine will probably be remembered for something else. So in 2018, she was, after more than 100 years of chemistry at Stellenbosch University, she was the first woman to be promoted to full professor in the Department of Chemistry and Polymer Science at Stellenbosch University. So, ladies and gentlemen, it is indeed a special pleasure to invite Professor Esterhuysen to deliver her inaugural lecture on intermolecular interactions, insight into chemical properties.
Good afternoon. So, one of the joys of becoming a parent is that you get to relive all those things that you enjoyed as a child. And as a scientist, the best thing is actually then to remember why you fell in love with science in the first place. So one of the first experiments that we did with my kids was this one, where my balloon has disappeared. This one. There's this one. When you take a balloon, rub it, get some static electricity going, and then you bring it close to a little stream of water. And as you can see, it starts to bend. Now, this doesn't just make 3-year-olds ooh and ah. My husband and I filmed this on Monday, and we were going, why is that so cold? Because what you can see is, I don't know if you saw it, but there were little drops of water actually jumping from that stream onto the balloon. And it feels like magic when you see it for the first time as a 3-year-old. And even as an adult, it's something special. But of course it's not magic, it's just science. So what's happening? We have a balloon, and when we rub it, we create static electricity. So what that means for a balloon is that you get a negative charge on the surface of the balloon. The water, on the other hand, we know is made of oxygen. Oxygen is an electronegative element, which means that it attracts electrons, okay? So it is very slightly negatively charged. So I'm going to use that little delta sign to show that it's slightly negative, okay? Now, there are a certain number of electrons on that water, so some of them are sitting near the oxygen. The other ones are going to be, or at least what's left over, is going to be slightly positively charged. So the hydrogens there are slightly positively charged. What you learn probably in about grade 3 or grade 4 is that if you have differently charged substances, they attract each other. So the water is then pulled towards the balloon. So this is one of the first things you learn as a child about science, is that you have an electrostatic interaction. This is not what you learn as a child. You have to wait until university to see that what's actually happening here is you have two differently charged species, and what influences how strongly those species are attracted to each other is the charges themselves, the sizes of the charges, and also the distance between them. So that's why you saw that when the balloon was far away from the water, that there was only a slight bend, and as the balloon got closer, the bend became more, because the interaction strength became stronger. So, what does this have to do with the topic of my talk? Well, I'm talking about intermolecular interaction, so this is what I'm interested in. And obviously, water doesn't just exist as one single molecule. Water exists as a liquid. Water molecules are tiny. Now, when I say tiny, what do I mean by that? I mean 1/10 of 1/1,000,000th of 1 millimeter is how big one molecule of water. So it's really tiny. So when you see those little drops of water jumping, what you're actually seeing is millions and millions and millions of water molecules. So there's something that's pulling those water molecules together. And what's pulling them together is very much what you see here with a balloon. Because one molecule is slightly negatively charged on one side and slightly positively charged on the other side, of course all molecules are like this. So that means that if you have a lot of water molecules, they're all going to be attracted to each other, and we're going to get multiple interactions. And I'm going to indicate the interaction with these sort of dotted lines like that, okay? And that dotted line means it's a hydrogen bond. So you probably have even heard about a hydrogen bond. It's one of those things that we learn about at high school. So when it comes to hydrogen bonding, we can define the various properties of the hydrogen bond based on, so we have a hydrogen atom which is bonded to a donor atom, and that donor atom is typically also, we've spoken about an electronegative element, so those are talking about the periodic table, those are the ones on the right-hand side of our periodic table, attracting electrons so that our hydrogen atom is slightly positive. And that's then interacting with another electronegative element on this side. So that dot shows it's a hydrogen, these dots show it's a hydrogen bond, and what we typically see is that this distance here for the hydrogen bond is fairly short. So this is relative to how far the molecules can get, or how close molecules can normally get to each other. So it's short. This typically gets longer when the interaction happens, and we have a linear relationship here, so everything's all in a straight line. So, electrostatics. This is, if you've done science at school, everybody's told you hydrogen bonding, it's an electrostatic effect. Positive, negative. But of course, that's not the whole story. So, we've only recently defined what a hydrogen bond is, 2011. So that's very recently. Okay, and yet they were discovered nearly 100 years ago. One of the reasons for that is because it's much more complicated than that. Okay, so let's say we have two water molecules close to each other. That electronegative element, the water, means that there are electrons that sit near to that oxygen. So there are our two little electrons. Electrons always work in pairs with different spins. And those electrons there, if this molecule gets close enough, those electrons can actually move from one molecule to another. Okay? This is one of the weird effects of the fact that electrons are what we call quantum mechanical particles. Okay? They have strange properties. So they can be somewhere where you're not expecting them to be. What we call this is charge transfer, and the other name for it is covalency, because when we have a bond between two atoms, that occurs because we have electrons that are being shared between those two atoms. We call this a covalent bond, so the solid line here is a covalent bond, and the fact that we have electrons now being shared between two molecules means that there is a certain amount of covalency. And if we have this kind of effect, that means that that's going to be a stronger hydrogen bond than we would have if we just had the electrostatic effect. Okay? Now, I've kind of drawn this in a bit of a funny way. It gives you the impression that that's all in a straight line, but actually, water, in the form of ice, forms multiple hydrogen bonds, okay, at all these funny different angles, and you can see that you get these rings of hydrogen bonds forming in ice. This is why ice is actually less dense than water, is because to maximize all these hydrogen, the formation of all these hydrogen bonds, you get the molecules sitting at a specific distance from each other, and that then means that the ice ends up being lighter than water. Why do they do this? Because they get extra stabilization. So if you just look at one hydrogen bond, so between two molecules, that has a certain, what we call interaction energy. So that's the strength of the interaction between the two molecules. And for water, it's around about 5.5, what we call 5.5 kilocalories per mole. Don't worry about the unit, especially those of you that are physicists, because it's not a proper SI unit. But if we look at the ring, if we take into account that one of these rings of hydrogen bonds, that's not, there are 6 hydrogen bonds, and the energy that's involved in that is not 6 times 5.5. It's about 10 times 5. It's about 50 kilocalories per mole. So you're gaining extra stability from the fact that you form these rings. Okay? So that's why water forms, or when it gets cold, it forms ice with these lovely rings, and why you get snowflakes with hexagonal patterns, because of that. So, but this is not all. There are other things that can happen. So for instance, we can get effects like polarization, which is also known as induction, which happens if we have a neutral molecule, and we bring a cation, so a positively charged molecule or atom near to it. What's going to happen is all of the electrons in the neutral molecule are going to be attracted to that positively charged ion, and you end up then getting slightly negative charge on this side because all the electrons have moved closer to that, and now it's an electrostatic interaction again. You have this attraction between this positive charge and the negative charge. So this can then make an interaction happen with a neutral species. An even more interesting effect that we see is something called dispersion. And this happens with neutral molecules, or can happen with neutral molecules. It can happen with anything. And this has to do with the fact that you have electrons moving. So if you have an electron, which is negatively charged, and you have another electron, which is negatively charged, and that electron, the first one, is moving, what do you think is going to happen when it gets close to this one? You're going to get repulsion, right? Because two negative charges repel each other. So this is going to start to move, and it moves away from the other one. And what ends up happening is that all of your electrons end up actually moving together. They're essentially running away from each other the whole time. And this we call correlated motion. So what happens then is as those electrons move, you end up at one point, you suddenly get an instantaneous dipole. So the electrons are all over here. In the neighboring molecule, those electrons repel all the electrons so that they go into here, and you end up with an overall positive charge on this side. So again, you have a negative charge, positive charge, and those two molecules attract each other. The next second, or the next instant, those electrons have moved on, and the negative charge is somewhere else, and there's another neighboring molecule that will be attracted to that, and so on. So this process goes on. All molecules undergo dispersion. Everything. Okay? What can happen is that if there's nothing else involved, so there are no electrostatic interactions, the only effect that you'll have is dispersion, so it becomes the most important effect. For neutral molecules, it is less important for things like where you have hydrogen bonding. Okay, so these are all the different types of attraction that you can get when you have two molecules that come close to each other. But of course, attraction isn't everything that happens. You get repulsion as well. Push it away. So we know that substances with like charges repel each other, they push each other away, but there's another effect, which again has to do with the fact, as I said to you earlier, electrons are quantum mechanical particles. So So I'm using the wrong word because a particle implies that you have like a little dot, like a marble that's moving. This is not a marble that's moving. This is an electron, which is also a wave. So quantum mechanics tells us that we can describe electrons not just as particles, but as waves. And when you have two waves that come close to each other, they can't be in the same space at the same time. So if you try and do this, this doesn't work. Okay? So the physics tells us this is not going to happen. And what that means then is that we have repulsion. So this line shows us, so if we start with two atoms infinitely far apart, and we bring them closer and closer and closer to each other, okay? And we move along this axis here. What's going to happen at some point is they're going to be attracted to each other by electrostatics, hydrogen bonding, charge transfer, dispersion, polarization. All of these things are going to attract those two molecules together, but at the same time, you have this Pauli repulsion, which is this quantum mechanical effect that the atoms can't get too close to each other, counteracting that, and at some point you're going to get to a minimum energy state. So this is what we find in nature, is that minimum energy state. So my work looks at trying to find what is the way that a molecule looks when it's in nature. And if we can understand its shape relative to the energy, then I can start to say something about the properties of those materials. Okay? So this is how it works for any kind of interaction. Okay? So what I'm going to do is I'm going to give you a couple of examples of from my work talking about specific types of interactions and how they are important for us in chemistry. So I've spoken about hydrogen bonding, but I want to mention another type of interaction which is called halogen bonding. Now, hydrogen bonding we all learn about at school, and it makes sense. We've got the negative and the positive and the negative, right? Halogen bonding looks very similar. So again, we've got a donor, we've got an acceptor, and we've got a halogen bond former over here. And this is a halogen atom. So halogen atoms, where's that? That column over there on our periodic table, it's electronegative, which means it's negative. So we have a negative atom, a negative atom, and a negative atom. What did we say earlier happens with negative atoms? They repel each other. And yet, we know, it's been proven for the last 15 years, that they don't, that under certain circumstances, this doesn't happen. They are actually attracted to each other, these molecules. How does this work? I'm going to show you something called an electrostatic surface potential. So this is an electrostatic surface potential. What it is we calculate what the outer edge of a molecule, where it will be, and then we look at what happens if we have a positive charge sitting at any point on this. So it tells us that at this point here, so the blue means that if we have something that's positively charged, it's going to be attracted inward, okay? And if it's red, it's going to be pushed away, repelled. So if we have this part of the molecule pointing towards this part of the molecule, you're going to have two negative points facing each other, and you're going to get repulsion. However, so these are all in the same family. So we have a carbon in the middle, we have three fluorine atoms on the outside, and then we have different halogens. So this is a fluorine, a chlorine, a bromine, and an iodine. And what you can see that as we go up, down the column, you can see that that iodine has a red bit there. The red bit means that at that point, it's not repulsive, it's attractive. Okay, so if we have a fluorine atom coming close to that, it's not going to be repelled, it's going to be attracted. So even though we have a negatively charged, overall negatively charged atom here, it can actually attract another negatively charged atom. So this is a very unusual effect. It took many years before people actually realized that this occurs. Sorry. It took a long time before people realize that this actually occurs, and it's a very important effect in our biology. A lot of medicines contain halogen atoms, and the reason they contain halogen atoms is because they interact in this way with the proteins in our bodies. So we've done some work looking at halogen bonding in triiodide species, but in the interest of time, I'm not going to talk about that. I'm going to talk about another very interesting interaction and bring the halogen bonding into that in a moment. So the other interesting type of interaction that people have become aware of over the last sort of 30 years is of interactions between gold atoms. So gold, on our periodic table, I'm a chemist, I have to look at my periodic table, there's my gold atom. So gold in a complex like this has a charge of +1, okay? So this is a gold atom, this is a gold atom, they both have charges of +1, so again, we're expecting that to be repulsive. It's not. They are attracted. These molecules are attracted to each other. How does this happen? It happens because gold is a weird element. Gold is electronegative, okay? So even though it doesn't sit on the right-hand side of the table, it's still electronegative, and the reason it is electronegative is because it's affected by relativity. So what happens? The inner electrons on gold are s electrons, and they move very fast. They move close to the speed of light. Because they move close to the speed of light, relativity tells us that they get heavier. Because they get heavier, they become stabilized. They have lower energy. Now, an atom can only have a certain amount of energy, so if the inner electrons are more stable, that means the outer electrons are less stable. That means they're further away from the nucleus, and they're what we call easily polarized. They can move around a lot more. And because they can move around a lot more, that means that that dispersion effect, you remember me talking about the electrons moving? So now you've got gold sitting there with 79 electrons. Now you've got 79 electrons loosely moving through space, so you're going to get this very strong dispersion effect. Okay, so that's what's happening, and that's why these gold atoms are strongly attracted to each other, despite the fact that they're both positively charged. So, but that's not always the case. So this is actually some work that I did with one of my PhD supervisors. His students synthesized this compound, and you see, if you look here and here, you'll see it's exactly the same, except here you have a gold-gold interaction, and here you have an interaction between a gold, and this is a chlorine atom, okay? And in this case, this gold-chlorine atom is the attraction is stronger. In most other complexes, this one is stronger. So computational chemistry, which is now what I'm spending a lot of my time doing, tells us why we get specific interactions. This is not a halogen bond. So remember I was saying that a halogen bond is an interaction between where you have a halogen. What's important there is that it should be a linear, so here, it should be linear, and in this case it's not. So that tells us this is not a halogen bond. This is an electrostatic, just a purely electrostatic interaction. However, the question is, could it be a halogen bond? Is it possible that such a species could form a halogen bond? And the answer is yes. So, but before we get there, let's take a step back. So we spoke about hydrogen bonds. Those are what you learned about at school. And the question is, can gold form a hydrogen bond? So in other words, remember, hydrogen bond is where we have an electronegative element with a hydrogen forming an interaction with another electronegative element. And I said to you that gold is an electronegative element. So this is actually not gold on its own, this is gold minus. And gold minus behaves very much like a halogen, so this forms a strong hydrogen bond. But gold minus doesn't exist very much on its own, or doesn't really exist on its own. It is usually in the form of a complex. So in other words, there are things attached to it. So here gold is in a complex. It has these two ligands. Overall, it's still negatively charged, but the gold itself is formally positively charged. And you can see it forms a hydrogen bond here with water. Okay? So again, gold minus is not very common. Even in a complex, it's not very common. So much more common in neutral compounds. So in neutral compounds, you have, we've also shown that gold can act as a hydrogen bond acceptor. So even though it's formally positively charged, it is actually behaving as though it's negatively charged to form this hydrogen bond. So what we also see is that we have a second hydrogen bond here. So this is a much more typical hydrogen bond, electronegative NHO. So these are very common in chemistry, this kind of hydrogen bond. This less so. So the question is this actually really, does this hydrogen bond really exist? And this is not a trivial question, because if we know that these hydrogen bonds exist, then we can start to utilize this information for things like catalysis, synthesis, and so on. So we're trying to understand what the nature is of this interaction, whether it exists, and what its nature is. So to do that, we've used several different approaches, and this is one where we looked, so this is now a different hydrogen bond donor. This is hydrogen fluoride. But again, you see it forms a hydrogen bond with gold, and again, you have the second hydrogen bond over here. Carbon is not such a strong hydrogen bond donor, so we expect this interaction here with the fluorine and the gold to be the same as here, but we expect this interaction to be weaker. And we can do things like this. So, Andre likes his graphs, I like my graphs. These graphs are what we call an energy decomposition analysis, and this tells us about the components of the energy. So we've spoken about those components. We've got electrostatics, we've got the charge transfer and polarization. So we put those, the two charge transfer and the polarization together in an orbital term. We've got dispersion, and we've got the Pauli repulsion. And these then tell us what the nature of all of those components is. So this is what's happening in this species. This one tells us about this one. And you can see here, the blue one tells us that this is largely an electrostatic interaction with orbital interactions also playing a role. However, that doesn't help us because we've still got the second hydrogen bond over here. So what I've done is taken this part of the complex out and just looked over here at this interaction here and this interaction here. This is much weaker as we would expect it, and this one is significantly stronger. But what you can see there is it's much more electrostatic. So the normal hydrogen bond that we would expect to see from what you've learned at high school and what's been known for 100 years is primarily an electrostatic interaction, which is the way you were taught it at school. What's left over, so if I subtract that from the overall picture, this over here tells us what's happening with the hydrogen bond with the gold, and it shows this grey part tells us that charge transfer, polarization, so the fact that we have electrons moving between molecules is much more important for this kind of interaction than for that. And that's good news, because that means that we can then use this kind of interaction for catalysis. So trying to understand how we can make reactions happen, where the first step is the formation of a hydrogen bond like this, is where we are now going with this. So to try and understand how we can utilize this for catalytic methods. We can also look at this by making pretty pictures. So this is a different computational chemistry technique that we use called atoms and molecules. Atoms and molecules tells us when we have bonds. So if you see a green sphere over here, that tells us that there's a bond. So It's difficult to see, but there's a green sphere in there that tells us that we have a hydrogen bond here. There's a green sphere here that tells us that's a hydrogen bond. But these sort of discs over here also tell us something about the strength of the hydrogen bond. So if there's a red color like that, that means it's attractive. If there's a blue color or green color like that, that means it's repulsive. Okay? So this is telling us that we have two interactions here. This one is slightly stronger than that one. So that means, again, that we can use this information to say something about the nature of these interactions. Because hydrogen bonding and halogen bonding are so similar, we can do the same with halogen bonds. So we can see from here, so these are different, on the right-hand side, different halogen bond donors. The iodine was the one that had that big positive part, so we expect that to have a stronger interaction. If you look at the halogens on our periodic table, you can see iodine is down at the bottom. That means it's the biggest. So we would expect that simply because it's got a big radius, that it would be further away from the gold. But you can see that here, bromine has a smaller radius, but it's actually further away from the gold, and the chlorine still further. So that means, when I said that, remember I said earlier that we have, when we have stronger interactions, we have shorter distances. That means that this is a stronger interaction than this one or that one. This one is much stronger than that one. You can see that by this length. This is an angstrom, so 10 to the minus 10, that's that 1/10 to 1 millionth of 1 millimeter in length that we're looking at here. What's important about this is not just that that distance is short, that this distance is long. So the iodine has already started lengthening. What does that mean? It means that we can then start to use this kind of interaction to do oxidative addition. So in other words, that iodine is so strongly attracted to the gold, it started to break from this one, which means that we can actually get that iodine to react with that gold center. Once we can do that, then we can start using this for what my colleagues always say, real chemistry. So this is much more, this is a fundamental kind of study, trying to understand what the nature and properties of these sort of unusual interactions are. But I also do work with a number of collaborators where we look at applying to different examples. So we have lots of different applications. I've spoken about catalysis, and there are many biological applications and so on. But the one that I like to talk about is when we look at the applications in porous materials. So what are porous materials? Porous materials are materials that have empty spaces in them. So at the moment it's not an empty space. You see there's something in there. So this gray part is something where there could be an empty space. These molecules over here are what we call the host framework. So this is a crystalline material that doesn't change very much, usually. And then we have small molecules. So these are our guests, which are typically gases or liquids, so solvents that we could be using, that can move in and out of this framework. Okay? And what's nice about this from my perspective, being interested in intermolecular interactions, is that there are so many things that I can look at. I can look at interactions between the guest and the host, which is very important if we want to look at applying these kind of things to having materials that can absorb gases. So absorbing something like carbon dioxide or hydrogen is very important for the green economy as ways of getting rid of carbon dioxide or from the atmosphere. So host-guest interaction is important, but there's also interactions between the guest molecules, so these are the molecules that are coming in that are sitting in those spaces, and then also host-host interactions. I'm going to give you just one example from the work that we've done to show you why it is that all of these factors can be important. So this is a copper glutarate molecule, so you can see it forms these chains, these one-dimensional chains. As it crystallizes, it has the chloroform that sit in channels in between those chains. What's interesting about this is it's what's called pleochroic, which means that if you have polarized light and you look at it under the polarized light, it's different color. It has different colors depending on what the angle is that you're looking at. So these are just two of the colors. There's a yellow and a red, but there's also a variety of blue and purple colors that come out. What this pleochroism does, it helps us to see some very interesting effects. So what I'm going to do is I'm going to show you what happens when we put this crystal into a different solvent. So it did have chloroform in it, and now it's been put into acetonitrile, and you can see that that acetonitrile is taken up into that crystal. Okay, so it's being absorbed into the crystal, and as it's being absorbed, it's changing color. So this allows us then to use this kind of material for sensors, so that we can see if that material is present, and obviously if we can make it in large enough quantities, which at the moment we can't make it in large enough quantities, we could then conceivably use this as a means of purification of for substances by withdrawing them from mixtures and so on. So this is what we're interested in doing, is trying to utilize these porous materials for practical purposes. Okay. But the question is, why does it change color? And why does it change color in such a weird way? I don't know if you noticed, it had this sort of hourglass shape. I'm going to show you another picture. So this is in two different solvents. So this is the acetonitrile, which I've just shown you. And you can see that it has this sort of hourglass shape where the liquid moved in to that hourglass first and then eventually filled up the whole crystal. You can see if we use nitromethane, the same kind of thing happens. Again, there's absorption first through sort of little bound triangles up at the top and the bottom. So this is a very interesting question. We were trying to work out why this was doing this. So the student concerned measured spectra, and these are the spectra of the empty compound, the original one as synthesized with chloroform, and then the acetonitrile and the nitromethane. And what these peaks tell us is what the color of the substance is going to be. And you can see the fact that they're shifted away from each other means that they all have different colors. So that agrees with what we were expecting. So what we were trying to do was explain why there is a difference. So we thought that what was happening was that there were host-guest interactions. Because the guests were different, the host-guest interactions would be different, and that would give the color change. So you can see here that this is the acetonitrile, and it's interacting over here with this ring. If we look at the acetonitrile again, it's also interacting over here. This is the nitromethane, it interacts with a different part. So host-guest interactions, but trying to calculate something like this gave us no information. Okay, so not host-guest interactions. How about guest-guest interactions? So here we've got in the acetonitrile, you can see there are different interactions here, head to tail, interactions over here, dipole-dipole, there are other interactions over here, these are different interactions. It didn't work, didn't tell us anything. Okay, so, and those are usually the first things that we look at. Host-guest interactions are usually what drive uptake of guests into hosts. So in this case, it turned out that it was actually host-host interactions. So what we have here, so this is the as synthesized one. This is the one with the acetonitrile, and this is the one with the nitromethane. And you can see that there's a little bit of twisting here on the host. Okay, so these interactions change slightly. So here we have slightly different interactions to here and to here. And it was these interactions that resulted in the color change. So what we did was we calculated the interactions involved when there was a tilting of that central ring. And if it's not tilted or if it's tilted, that changes the orbitals that the electrons are sitting in. So this is where they're an empty orbital, this is a filled orbital, and when you get a color change, what's happening is you have electrons jumping from one energy level to another. And the energy level corresponded to a change in that tilt of that ring. So that then explained why we were getting this color change. It was simply a fact of the host framework tilting and undergoing different host-host interactions. But why does it go up into that funny sort of triangular shape? Well, that was an entirely different question. So what we did was we calculated where the channels were. You can see the channels run like this. Okay? And using crystallography, we can determine what surface is. These two surfaces are. We give them specific names. This is just the name of the surface. And we can then go and calculate how the substances are moving into those channels. So this is this surface down the side, okay? So we're wondering whether the molecules are moving in from that channel or from the top. This is the side, this is the top, okay? And these energies here tell us what is the energy involved in that molecule moving into that channel. The larger the number here, the more the stabilization. So that means that both of the solvents are far more attracted to the top surface than to the side surface. So they move in from the top and not from the side. So that was exactly what we were seeing. We were seeing the molecules move in from the top. However, we would expect that to just give a straight line, so we would expect the molecules, to see the molecules moving in a straight line along here. And we don't. We see this very strange hourglass pattern. What is going on here? It's something very trivial. It turns out, when we have a small crystal, it doesn't do this. It does this. The big crystal, it does. And if you look at that big crystal, it's got a funny shape. You see it's got it looks a little bit like a bow. It's not one crystal. Actually 4 crystals that have grown together like that. So as the crystal gets bigger, you get this growth pattern. And so what's happening is these two sit. So one crystal sits like this. The other one on the other side is flipped. This one is flipped so that the channels run this way. And that then explains why we end up getting the molecules moving from this side, and from this side, from this side, and this side, giving the overall hourglass shape that we saw. Okay, so this is just as a result of crystallization. Again, that has to do with interaction between the host frameworks as they crystallize, but how they move in, that's then host-guest interactions. So there are a whole bunch of interactions that we had to understand in order to explain what was going on here. So this is the type of interaction that we can, or the type of information that we can then use to go further. Once we understand how these things work, we can then go and start to predict new molecules that will have better properties when it comes to things like taking up solvents, taking up gases, and so on. So that is the next step, to take this information, not just explain what's going on, but start to predict. So in closing, I want to end with the way that most of my calculations that I do using the program, I use a computational chemistry program called Gaussian, and Gaussian always tells you when you've done something right, because if you've done something right, you end with a little quote, a little Gaussian pearl of wisdom. So I'm going to give you a final Gaussian pearl of wisdom, which is from an anonymous writer. And he said, "Man, despite his artistic pretensions, his sophistication and many accomplishments, owes the fact of his existence to a 6-inch layer of topsoil and the fact that it rains." I would like to take it further. I hope that I've managed to show you that it's not just that it rains, but because rain is made of water, and those water molecules are pulled together by intermolecular interactions, that we have intermolecular interactions. So just to end, I need to acknowledge, like Andre, people who have done all the work over the years, so these are all the students. I particularly want to highlight the two examples that I gave today were done, so the gold work was done by Fabio Grunewald, and the porous material work was done by Charles Seidenote. It's one of my absolute joys in this job to see students coming in, particularly those that I know as undergraduates, and see them grow and leave here as scientists, real scientists. And I'm very, very proud of all these people. They've made my job so great. What also makes my job great is the people that other people that I get to work with. So these are my collaborators and my mentors. I particularly want to highlight those people who have been absolutely instrumental in my career. My PhD supervisor, Gert Kruger, who was he's my mentor as a PhD. My early career mentor was young Dylan, so I'm very grateful to him. And my sort of middle establishing career has been Len Barber. He has he helped me through some really tough times when I was a young mother and trying to balance motherhood and research and all of that. So I'm very grateful to him, and I'm grateful to all of these people as well. The people that I have not put on here are actually the people who are the most important. That's you guys, my friends, my colleagues. It's been wonderful working here, and it's been wonderful knowing you, and particularly all of those friends who have jumped in and helped with looking after kids and giving me a hand when things have been tough. I'm so grateful. My colleagues and my friends, and that is a wonderful experience. And then, of course, my family, my parents, who raised me, who made me excited about science, who still make me excited about science. I'm very, very grateful for all your love and support over the years. My mother-in-law, who's been willing to jump in when I have gone overseas to come home, to come and help my husband with raising the kids. Although not that he needs help, he's a fantastic father and husband, and I'm truly grateful for everything that he's done. He and the kids have sacrificed a lot for me to be here, and I am so grateful. Thank you so much. And thank you for your attention.
The other person we need to thank is Catharine Esterhuysen. Catharine, of course, is a physical chemist. Unfortunately, in South Africa now, physical chemists are becoming increasingly rare. So we're extremely lucky and proud to have Catharine as a member of staff in our department. And as you saw, her work on computational methods to investigate and understand fundamental interactions, halogen bonds, interaction and bonding in gold, really has made a fundamental contribution to the understanding of how these types of interactions work. And Catharine gave a very, very nice example of how applying this to supramolecular chemistry. So Catharine, we also expect and hope and know, in fact, that your contributions in this regard will continue over the next few years, and certainly we look forward to that. Catharine is also known as an outstanding teacher, as Louise mentioned. I'm always amazed, if you've ever done physical chemistry, which I think many of you have, it's often seen as the most difficult part of our chemistry undergraduate curriculum. And somehow Catharine still manages to get some of the best teaching reviews that you get in the department. So that's really quite outstanding. And Catharine, I will say this, I speak for all of your colleagues when I say that we all respect you for your hard work, your complete fairness, and then something that's really important, her compassion Catharine is really somebody who, no matter what goes wrong, what happens, she has that compassion and that approach, which I think is really an important thing. And I must say, as head of department, I rely very, very much on Catharine's wisdom and guidance in many cases, which are really difficult. She has this knack of being tough and wisdom, but does it with compassion. So Catharine, I must say, we really appreciate that as your colleagues, and certainly I appreciate that as the head of department as well. So I'm sure Matthias, Fleur and Sebastian are very proud of their mom. Certainly we as a department are proud. I must also say Catharine is probably my oldest friend in the department. So congratulations from my side as well. So that's more or less it for the evening. We are in the first year lecture facilities, and this complex has lecture halls plus the undergraduate laboratories. I'm pleased to say that we have an assignment and a practical for you after this. You've heard and had a discussion with regards to wine and the various components. There's about 800 volatile compounds in a pinotage. The task for you now is to go downstairs and try and identify and see whether you can identify some of the 800 different compounds. So please join us downstairs.